so recitation for November 1st. There are 6 problems in this recitation. Right now, first one is Chapter 10, Question 30. And the question is, a uniform 2 kilogram solid disk of radius r equals 0.4 meters, so this is the solid disk here, is free to rotate on a frictionless horizontal axis through the center. The disk is initially at rest, which means the velocity of the disk initial is 0. And then a 10 gram bullet is traveling at 500 meters per second and is fired into it, as shown here. If the bullet embeds itself at a vertical distance 0.2 meters, another way of saying that is r divided by 2, above the axle, what will be the angular velocity of the disk? Right, so L here, the length from the distance from where it is to the axis is going to be r equals over 2, and then we're trying to find W final, right? So there's no external torque, there's no friction, nothing like that, which means that L1 is equal to L final, so that's the angular momentum initial is equal to the angular momentum final. And then we can use this equation here, L equals mv cursive L, and so then that would just be, the mass of this one, so mass times velocity times cursive L. And then we'll use L final equals the inertia final times the angular velocity final. But remember, we have 2 things that have inertia. Now we've got the bullet and the solid disk, right? So the disk we know is going to be 1/2 capital M capital R squared. That's the inertia of the disk. That's just a given. They'll give that to you in the problem if they don't have it on the formula sheet. Plus the inertia of the bullet, which is going to be ml squared, right? And then you plug in all of your numbers, and you'll find that it equals to 0.1604 is equal to the inertia, right? And then you set the 2 equal to each other here. So you've got mvl equals I final, W final. You've got right? Divide all of this by inertia here, and that gives you W final, which is 6.23 radians per second. So that's that problem. And we'll move on to the next problem. Yep. Okay, let me read it out. Okay, Atwood's machine. Figure 1077, I've tried to draw here, illustrates an Atwood's machine. Find the linear acceleration of blocks A and B, the angular acceleration of wheel C, so you're finding the acceleration of this block, acceleration of this block, then you're finding the angular acceleration, and the tension in each side of the cord. So tension on this side, tension on this side. Yeah, let me calculate that down here. Oh, if there's no slipping between the cord and the surface of the wheel, let the masses of blocks A and B be 4 kilograms and 2 kilograms, respectively. The moment of inertia about the wheel is 0.3 kilograms times meters squared, and the radius of the wheel is 0.120 meters. Right. So that's the question. So first we'll kind of draw free bodies from each of these points. And essentially what you're going to be doing is you'll find, okay, so here this is going to be using the sum of the forces equals mass times acceleration. That's the formulas you're using here. And then here you're using the sum of the torque equals inertia times angular acceleration, and then you'll be kind of using that to work all of it out. We'll just do it. Okay, and remember that because block B is connected to block A by a string, then the acceleration of A is going to be equal to the acceleration of B, because they're going at the same rate, right? So A and B's acceleration is the same. So from this side, free body diagram, you've got acceleration. We're going to say it's going to the right, so up and down from left to right. So from A's perspective, acceleration is going down. So right here we have the mass of A times gravity minus the tension of A going upwards equals the mass times acceleration. Right. And then we do the same thing over here. So this is equation 1, equation 2, equation 3. Over here, we know tension's going up, but now acceleration's going up. So tension minus mass of B times gravity equals to mass of B times acceleration going up here. And then we switch over here to this free body diagram of the circle, of the disk. And we know that the mass times gravity is going down, and the tension in the forces are going down, right? Because they're being pulled down by these two blocks. And then you see that the force is going upwards so that, it doesn't just fall down to the ground. There has to be a force balancing it and keeping it in equilibrium. And then we say that the sum of the torque here is equal to inertia times angular acceleration. They give you that in the equation sheet. And now you substitute angular acceleration equals linear divided by radius here. And the sum of the torques is, because it's going this way, right, you've got the force going here, the perpendicular force, times the distance to the axis, to the axle here. So this one is, right, so the tension is going this way. This is the torque. And so we're going to say that this way, clockwise, is positive, since this is going to be the way the acceleration is going. And this one we see is going the opposite way, because it's pulling this way. So we're going to say that that's negative. So sum of the torques, we're going to say positive minus this one. So tension A times radius minus tension B, radius, equals da-da-da-da. And now at this point, we've got these three equations and we combine them all. So this is going to be the base, and we're going to substitute, we rearrange this to have TA on one side, move this one over here, and substitute now the left side into this equation for TA. So we're getting rid of TA, and we can see that over here. That's this part here, right? And probably shouldn't. Here, right. Yeah. Here. Oh, it's not good. Okay. So that it doesn't confuse y'all. Here, right. Got ours over here. And then we divide both, or all three sides by r to move the r squared over here. And then we combine, kind of place the g's together, place the A's together here, and then you'll add this whole section here, so you know that A is included in that, to both of these sides, right? So we see that. And then basically you divide this whole side by everything outside of A. So you take A out of these equations, right? And so then you've got A on this side, and then on this side, mass of A minus mass of B times G all over I divided by R squared plus MA plus MB over here on bottom. And you plug in all the numbers, and then it gives you 0.73 meters per second. So that is the acceleration, right? Now, it's asking for the centripetal acceleration, sorry, not centripetal, angular acceleration here of the circle disk. So you know that angular equals linear over r, so then calculate that. Tension, you'll just plug in all of the numbers for this equation basically, that's just rewritten here. And then you plug in all the numbers, and yippee, you're done. So now we'll move on to the next question here. Right, 10.62. A uniform 8-meter 1,000, where am I? There you go. 8-meter 1,500 kilogram beam is hinged to the wall and supported by a thin cable attached 2 meters from the end of the beam, from the free end of the beam. The beam is supported at an angle 30 degrees above the horizontal. Here. A, make a free body diagram of the beam. So first we'll do that. We know that the beam is stationary, so we see here we've got the torque, tension going this way and pulling a torque in a counterclockwise direction. And then you've got mass times gravity, right? We can, since it's uniform, it's going to be at the center of the beam, and you just put that downwards. And over here you've got Fy at the axle going upwards, right? And then you've got right upwards because it's following the torque direction that has to go the opposite way. It's this one. So that it's at sum of the torques equals 0, and it's not rotating. Originally, you would not know, like if you didn't know how to use torques, then you wouldn't know if this is going up or down, because tension is going up, so it has a vertical component, but mass times gravity is going down. So you don't know which one is bigger initially, because you don't know tension, and that could be bigger than mass times gravity, right? Or the vertical component of tension could be bigger, or it could be smaller, and you don't know originally. But we know that it has to be going up because the torque, this one, is going that way, and so to even it out, this torque has to be going this way, and so force has to go that direction. Hope that makes sense. Okay, so that's the free body diagram. Part B, find the tension in the cable. So tension equals what? Sum of the torques equals 0, like we said before. And here we just kind of draw out our diagram here. So we see that this distance from where the line, the wire connects to the wall, and the axis, that's going to be cursive LT. And so we see LT equals this number over here, right? You can do the calculation if you want. And the sum of the torque, the torque of tension is, since we're considering this to be positive, it's going to be the positive here tension, so the force, right? And then times the distance here. And then, yeah, so now you have T times this number that we calculated. Okay, so we know that there is a torque for gravity, and that's going downwards. So we say, right, so the perpendicular component to that here is going to be the LG. So mass times gravity. Yeah, okay. So LG equals yada yada. Torque equals negative, right? Because it's going in the opposite direction. Here, we can put that in the parentheses here. You can put this in the parentheses. Mass times gravity times cursive LG equals yada yada, right? And then we see that the sum of the torques equals 0, right? So this one here plus a negative number over here, right? But we'll move that to the other side so that they're both positive. And then you divide this whole side by this number, you get tension equals 13,200 newtons. Part C is how hard does the beam push inward on the wall? Right, so how hard does this beam push that way? So we need the vertical and the horizontal components of that, right? So the vertical components are designated over here by y, and then the horizontal by x. We see that the y is going to, the y is going to be, right, mass times gravity minus the upward tension force, which is going to be T times sine of 10. Right, it's sine of 10 because, as I've drawn here, right, whenever you see a z, you know that this angle and this angle are the same. Right, so then you've got 30 degrees down here that we saw up here, and then that's, if you draw the z, right, then it's going to be 30, and then that other one is going to be where you find this component here, which is going to be the y, kind of the tension y going upwards. And yeah, so that's why it's 10. Then the x component is t cosine 10, right? That's this one here vertically. Can't really draw that because it would mess up the diagram. And then we know that the force is going to be the y component squared plus x component squared, right? If you remember your, I guess, trigonometry or algebra or something like that. A squared plus b squared equals c squared, right? And so you plug in all the numbers, and then you get 18,000 newtons. That's that. Then, chapter 11, question 30. So let me flip to that question. Okay. Oops. All right. You are watching an object move in simple harmonic motion. Yeah, so simple harmonic motion. SHM. Shm. When the object is displaced 0.6 meters to the right of its equilibrium position, that means that x is equal to 0.6 meters, right? And we say positive because it's to the right usually. Usually to the right is positive. It has a velocity of 2.2 meters per second to the right, so that's going that way, and an acceleration of 8.40 meters per second squared to the left. Right, so it's, I didn't really draw a diagram, but here I can draw that. We'll pretend it's a spring. It could be a pendulum too, though, so it could be going this way that way or that way, or it could be going this way and that way. Right, either one. Both of them work in simple harmonic motion, or it could be, I guess, whatever else works in simple harmonic motion. Yeah. So then we'll just pretend that's equilibrium, and this is equilibrium. Although that looks slanted. Whatever. Okay. What's the question? How much further from this point will the object move before it stops momentarily and then starts to move back to the left? Right, so it's asking what's the difference from this position to the full amplitude. And remember, amplitude is the distance from the equilibrium point to the point where it stops and moves back, right? So it's asking amplitude minus 0.6 meters, because we've already moved 0.6 meters, equals what? So, to begin with, we will just kind of jump right in. So we know that 1/2 mv squared plus, right, so that's the velocity of the object, and we're just gonna kind of going to pretend and just work with this block here right now. So the kinetic energy of the block, right, plus this kind of elastic energy. Right, so this is kind of kinetic, linear, hopefully that makes sense, and then kinetic, elastic, and then equals, right, the kind of the basically kinetic total, right, energy, or the maximum kind of kinetic energy that it will have at any point. I believe that all of these are on the formula sheet. If they're not, then they'll be in the problem, but I'm pretty sure they're in the formula sheet. Right, this is what we've got, and then we rearrange all of that to put A on one side and this over here, and then we use the sum of the forces equals mass times acceleration, right? So mass times acceleration equals, right, and then this is the force, kind of the kinetic, sorry, not kinetic, elastic force kind of equation for spring sort of thing. So that's the spring constant times the x that's displaced, equals that, and then you rearrange this to get m over k equals negative x over ax, and then substitute that in here because we don't have m or k, and so we use this to basically not need it, and then put this in its place. And then we have all of the components calculated out, and then you have to remember to minus 0.6 from that, and so this is your answer. Yep, okay. Let me know if you have any questions on that, obviously, as always. Let's see. Let's get one. Okay, maybe that works. Okay, 11.36. Let's see, which question is this? A mass of 0.2 kilograms on the end of a spring oscillates with, okay, so right, I drew the diagram here, oscillates with an amplitude, oh wait, sorry, with a period of 0.45 seconds, right? So t, I wrote that as t, but let me write that as a better t, I guess. I'm gonna write that as a lowercase t so that you don't think it's tension. I put it anywhere else? No, I don't think so. Okay. So, oh wait, here. Here it is. Okay. T equals 0.45 seconds. There's 0 there. And an amplitude of 0.15 meters. Find A, the velocity, when it passes the equilibrium point. Right, so whenever something passes the equilibrium point, you know that that's going to be the maximum velocity it can have. So just something to remember. B, the total energy of the system. C, the spring constant. And D, the maximum acceleration of the mass. Okay. So, kind of in this dotted line is actually the calculation for the spring constant, because we're going to need that later on. So I'll go back to it whenever we need it. But it's kind of out of order. Sorry about that. Okay. A. The velocity when it passes the equilibrium point, so maximum velocity. Right, so we've got 1/2 mv squared max is going to equal the total possible kinetic energy. Remember, we used that before. So 1/2 spring constant k times the amplitude squared. And so then you rearrange that, get v on one side, amplitude over here, then you, oh, right. And then you're stuck with this k here, right, that you don't know. So you go back and remember that the period equation is t period equals 2 pi square root of m divided by k. And since you have all of these components except for k, you just rearrange the equation. K equals m 2 pi, that whole thing squared, divided by the period squared. I hope that's obvious that that's a squared. Okay. Let me. Just a second. Don't want to confuse anyone. That would not be good right before a test. Okay. Hope that's better. And then that gives you 39.0 newtons per meter, right? And so then you can just input that here, get the number. B, it's asking for the total kinetic energy, right? So total kinetic energy is going to equal, right, the equation that we just used again. And so calculate that whole thing. C is finding the spring constant. We just did that. So we're done with that. And then D is asking for the maximum acceleration. So here just remember, right, force max is equal to the mass times acceleration max is equal to k times a. So, right, because if you remember up here, we saw k, right, so force is equal to the k times x. So whenever the distance is at the maximum, right, so a is the maximum displacement that the block can have from the equilibrium point. So whenever that's at max, then you know that the force is also at max. And I guess think of it as like a rubber band. If you stretch it out the most you can, then that's going to be the most difficult it is to hold it in place, right? Whereas if you only stretch it a little bit, then it's not going to be difficult. Not going to be so difficult to hold it out, right? So the maximum displacement from equilibrium is the amplitude, right? So then you just, right, work on this side of this equation, divide k amplitude by m, and you get maximum acceleration. Here, just make sure that y'all can see that. Okay. And then that is your equation. So then we have one more question to go. Okay. This one is okay. 11.58. A block with mass m rests on a frictionless surface and is connected to a horizontal spring of force constant K, the other end of which is attached to a wall, a lovely wall right here. Okay, this is what we've got. Excuse me. A second block with mass m rests atop the first block. Right, so we have little m and big M. The coefficient of static friction between the blocks is mu sub s. Find the maximum amplitude of oscillation such that the top block will not slip on the bottom block. So it didn't give you any numbers, right? Which means that your answer is going to be all in symbols. As you can see, all of this is in symbols. Right, so it's asking for the maximum amplitude such that nothing slips, right? This is your free body diagram, right? You've got mass times gravity going down. This is at the top block, right? And then you have the force, the frictional force, right? Going that way or that way, depending on which way, you know, it's oscillating from. But we'll just pretend like it's going that way. And then you also have the acceleration going that way. And so, all right. You've got the normal force. Sorry, not normal force. Yeah, normal force. Normal force N is equal to mass times gravity, right? And so then the frictional force of static friction, so that it's not, you know, moving, right? We don't want to overcome the static friction, is going to be N times mu sub S. And so then, you know, that's going to be mu sub S times mg, right? From pulling that down here. And then you see that the maximum friction of static frictional force is equal to this force here, right? That the block is going to have, because if this is bigger than this, then static friction is overcome, and then the block's going to slide. But if it's less, then it's not going to be the maximum, like, amplitude, and not going to be the maximum frictional force. So they have to be equal to each other. Right. So just kind of remember that, basically. So we've got mass times acceleration from F, and frictional force, right, so maybe, there we go, is mu sub S mg. You can cross out both of those m's. And so now you have mu sub g equals acceleration. Right, and so you know that force max is here. You don't need to write that, but just, you know, so that you know the acceleration is the maximum. Right, so F, the force, right, and here I just abbreviated to X, but max, that looks like gibberish. Okay, we're just gonna leave that as that. Okay, just know that those are the same F's, right? Same F. It's gonna be K times X displacement, right? Right, so the force here that's associated with the spring is equal to all of the masses, right, times the acceleration, because the spring is working on the whole thing, right? Not just the bottom part, not just the top part. It's working on all of it together. So the masses have to be summed. Since this is the spring and this is related to the spring, right? Whereas this stuff up here, we only used the small m because it was all in relation to this free body diagram. Okay, so A equals A max, right? As we said before, when the x, the displacement from the equilibrium, is equal to the amplitude, right? So then A max equals, right, this thing down here again, mu sub s g equals ka over m plus this one here, right? So this is just this, and then a is moved in, subbed in for that. Divide this whole thing by m plus m, and then you've got a equals this thing here. At this point, you forget about a in the middle, set these two equal to each other, divide this by this kind of section, and then you have amplitude equals this thing. So that sums up the recitation from today. I hope you learned a lot. If you have any questions, feel free to email me. Yeah, good luck on your test.